Hi there, Mr. H here. Gonna take a look at 7.4, more identities. Woohoo! These are double angle and half angle identities. Just more identities that you're gonna see in calculus and use for a variety of applications. All of these identities, we're gonna start with the double angle, are derived from the sum identities from the previous section. So just to give you a look of how that works, they're pretty easy to derive. I've written down the sum identity for cosine, and really all you're doing is letting A equal B, or just replace all the B's with A's. So your two angles are the same, right? So then that's going to be cosine of A plus A equals cosine A minus sine A, sine A, lots of A. Okay, and then simplifying that, A plus A is 2A. And then cosine times cosine is cosine squared, and sine times sine is sine squared. Right, so that's how that first one is derived. It's really just a special case of the sum identity. The second one down the list is then you can replace sine squared with 1 minus cosine squared, right? So in other words, right here, we keep on going. Instead of sine squared, the Pythagorean identity, a version of that, is 1 minus cosine squared, right? And then just simplify that. What happened there? Right? If I distribute that negative, it's going to be a plus cosine, and cosine plus cosine will be 2 cosine, and then minus 1, right? Okay, and then this one would be, similar, but just go back to this one and replace cosine with 1 minus sine, and then you derive that one. Right? The sine 2a, you would start with the sum identity for sine. So if you wanted to try that one out, just think about doing the same thing as we did here, but just with the sum identity for sine, and you'll see that you get what's shown there. And then it's also for tangent. Just go to the sum identity for tangent and replace all of the B's with A's and simplify. Okay, so I won't do the rest of them. Give you a heads up though on how you could do it if you want to try it out on your own. Take a look. But let's jump to some examples that you're going to see in the homework now. Some double angle identities to solve these problems. The first type, notice the structure. It's probably going to match one of the identities, and just use that identity in reverse. So this one I have cosine squared 60 degrees minus sine squared 60 degrees. That's that very first one. There it is, right? So I'm just going to use that version of it. It's cosine 2 times 60 degrees, right? So this is equal to cosine of 2 times 60, right? Which is 2 times 60 is 120. And then that is a value on the unit circle. So we'd have to take it one step further. It's in the second quadrant. So I know cosine is negative. And then at 120 degrees, that's equal to 1/2 for the x value, right? So refer back to your unit circle for that. Okay, so there's your answer. Right. I guess you could plug that into your calculator too and verify that that's equal to negative 0.5. Okay, how about this next one? 2 cosine squared minus 1. There's just another version of that double angle identity for cosine. It's that second one down that we saw, right? So that also is equal to cosine 2a, right? This one just happens to be in radian mode, but this is going to be cosine times 2 times 3 pi over 8. Okay. And then multiplying that out, 2 goes into 8 4 times. This is cosine of 3 pi over 4. And 3 pi over 4 is on the unit circle. 3 pi over 4 is the same as 135 degrees. Again, quadrant 2, negative. And then that's that one that's root 2 over 2. Okay. moving right along. This one is a tangent. So if I look at the identity, let's see, it's that last one, but this one has a 2 in it. So I got to be a little bit careful here. And that expression does not have a 2. So let's rewrite this identity and see how we can fix that. So the identity is tangent 2a equals 2 tan a over 1 plus tangent squared a. Right? Oh, sorry, minus. What am I doing? Okay. Minus. Okay. So this expression does not have that 2, but I can manipulate this identity. I can multiply both sides by 1/2, or to get rid of that 2 on this side. Right. And then that's going to cancel that 2 out. And I have now 1/2 tangent 2a is now that expression is exactly what's given, where a is 8 degrees, right? So I'm going to write this side, okay, just replacing a with 8. Okay, so I have 1/2 tangent 2 times 8 degrees. And 2 times 8 is 16, so I have 1/2 tan 16. Now 16 is not on the unit circle. We want the exact value, so we're just going to stop there. If you can't use the unit circle, just leave it as the expression, and that'll be the answer. Okay, the last one looks similar to the sine double angle. Sine 2a is 2 sine a cosine a, but again, this one doesn't have that 2 out front. So I can manipulate this, divide that 2 to the other side. Here's a alternate version of that identity, just using some equation operations there. Okay, so I'm going to use this form for my simplification, right? Where a is pi over 13. Okay, so I have 1/2 sine 2 times pi over 13. Which is just 2 pi over 13. And that's no special angle, so I would just leave it. And that's the answer, okay? The next type we're going to look at is when, it's kind of similar to 7.3, you had some given information, but now you have to find other things. You're going to apply the identities, right? So for part A, cosine 2 theta, notice what's given is cosine. So you have lots of different versions of that cosine 2 theta. Use the one that just has cosine in it is probably your best bet, right? So again, I'm talking about these 3, right? You have all 3 of those to choose from. This one is the one that just has cosine. The other ones have sine, which you could use, but then you'd have an extra step of finding sine A first, or sine theta in this case. So let's use that middle one, 2 cosine squared minus 1. Okay, and now all I have to do is just plug in the 1/5. Right, cosine theta equals 1/5, and there's my expression. So this is going to equal 2/25 minus 1. Okay, which I guess I could write that 2/25 minus 25/25. Okay, so that's going to be negative 23 over 25. There's the cosine. All right, how about for sine? Now we only have one version for the sine. It's 2 sine theta cosine theta. Well, in this identity, I have the 2. I don't know what sine theta is. I do know cosine theta is 1/5. So the problem here is not knowing sine theta. So I will have to go and find that. what I do is a quick drawing, right? Maybe over here on the side, let's see, if cosine is positive, but sine is negative, that must mean you're down in quadrant 4, right? So 1 and 5 is the cosine. Find that y value to figure out the sine. That's Pythagorean theorem. So 1 squared plus, this is just some margin work here. Right. And if you solve that, you're going to get 25 minus 1 square root 24, which actually can reduce because 24 is 4 times 6. You can take the square root of 4, which is 2. So that's 2 root 6. Okay, so the sine is 2 root 6 over the 5, right? Y over R. So that's what I'm going to put here. 2 root 6 over 4. Not 4, 5. The hypotenuse is 5. So that's y over r, which is the sine, okay? And now simplify this, and we've got our answer. So 2 times 2 is 4, so we have 4 root 6 all over 25. 5 times 5, 25. All right. Part C, tangent theta. Anytime you get to tangent 2 theta, you're going to have 2 options like the last section. You could use sine 2 theta over cosine 2 theta if you have them, which is usually the easiest, or you can use the identity, the one above, right? So since we already have cosine and sine, I'll just do that. Just make sure you use the 2 thetas, right? Tangent 2 theta is sine 2 theta over cosine 2 theta. And sine 2 theta is the 4 root 6 over 25. Cosine is negative 23 over 25. Invert and multiply, which just basically means those 25s cancel. And we're good to go. So this is going to be 4 root 6 over 23, all negative. Okay. And we've got it. So that's the end to that one. All right. And that's okay. That's a good stopping point. That's all of the different types of problems you'll see with the double angle identities. In the next video, we'll tackle half angle identities. Okay, send questions my way if you have any. Hope all is well. Bye.